am. I've got 1 o'clock, so we can go ahead and begin.
Excellent. I'm ready.
Okay, go ahead.
All right. It's a real pleasure to have today here Dr. Kush Varshney from IBM Research and Thomas Watson Research Center in Yorktown Heights, New York. Dr. Varshney graduated actually from Cornell University, and in 2004, and then he subsequently graduated, got his MS and PhD from MIT. And full disclosure, he's actually a former member of a former research group I was at MIT, and also the same lab, LIDS. And he's currently a staff member, research staff member in the Business Analytics and Mathematical Sciences Department at the IBM Center. And he's also, he's been visiting student at École Centrale in Paris. For those of you who are familiar, École Centrale is one of the prestigious grandes écoles in France. And he was also an intern at Lawrence Livermore. He's a member of Eta Kappa Nu and Tau Beta Pi, IEEE and ACM, and he's also won several awards, among them the Best Paper Award for Information and Fusion at the IEEE Conference on Service Operations Logistics, and he's had also an impact, obviously, receiving several awards also at IBM, and he's also a member of the associate member of the editorial board of DSP. It's a pleasure to have you here, and thank you and welcome.
Thanks, Amit, and yeah, thanks for the invitation to have me here. So yeah, the topic of the talk is learning classification rules via Boolean compressed sensing with application to workforce analytics. So the talk, at least the first half maybe of it, I'm just going to be kind of a high-level view of sort of the business analytics sort of field just in general, to maybe because for people studying electrical engineering, this is a kind of a new thing for us to get into. So I just wanted to give some highlights or some background on what it is that sort of the business applications bring. And then the rest of the talk, I will go through a new method for learning classification rules that's based on ideas of sparsity. So that work is jointly done with Dmitry Melyatov. All right, so as I mentioned, so I will just begin with just a high-level view of business analytics, what it is. Then talk about a specific problem that we've looked at, which is proactive retention, which I'll explain when we get there. And then I'll talk about this method of learning interpretable classification rules. All right, so just some pictures to get us rolling. So some businesses these days operate in the same way that they always have. So this is a Chinese medicine shop as an example. So in the first, second century and today, they're pretty much operating the same way. Similarly, this is a spice shop in India. Again, nothing has really changed in the way they operate. And also in France, these stores like these are more or less the same. So now there are some businesses these days that are starting to use data in what they are doing, but oftentimes it's just kind of collecting and examining data and just putting up some some bar charts in the background, which is not what we're really interested in at this point, but it's a step towards what we are interested in, which is businesses that are integrating data-driven algorithmic recommendations into their decision-making processes. So these are the organizations that are adopting business analytics from what I'm, in the sense that I mean. So business analytics is all about the decisions that go into running a business. So it's different from like quantitative finance and investing in stocks and other things like that. So really, it's all about hiring and retention and attrition and buying, selling, marketing, stuff like that, and strategy decisions that businesses make, staff deployment, and so on.
So this could be also something like for credit card companies, you have tons of data. Do the people, on average, under these conditions, default or not?
Yeah, that would be another example. Yep. Yeah, so I mean, just in the general field, I mean, anything where you're trying to make business decisions based on a large set of data that you've collected would fall under this, certainly. And yeah, please do stop me for questions at any point. Okay, so the field, which is still evolving, and I mean, it's kind of nebulous what it really is or isn't, but this is my view at least. So it's encompasses methodologies from applied math, applied probability, applied statistics, computer science, signal processing, etc., for using data to gain insight into business performance and to inform business strategy and so on. So the solutions are primarily used as decision support systems or as components thereof. So again, to inform business leaders into what sort of decisions that they should be making. And it's a bit different than operations research. And this is, again, my view of it. So I view OR as a technical area studying constrained optimization. And then management science being the application of OR to business, where, I mean, OR could be applied to like military planning or other things also. And my view is business analytics is the application of these signal processing or these other things to business. Okay, so just to give some examples of the types of business decisions in addition to a credit card company figuring out the defaulting.
Drawer is very interested in money.
Okay, great.
So is better at making it.
So how likely is a client to buy a product? Which product should we recommend next? What's a realistic view of opportunity by client? So your opportunity being an example is what they call wallet estimation. So you walk into a marketplace. If the seller in that marketplace knows how much money you have in your wallet, they can better kind of sell stuff to you because they know exactly up to how much you can spend, so they won't show you stuff otherwise. So that would be a view of opportunity. So are there accounts where there's significant untapped revenue, for example? Which clients are at risk of moving towards competitors? What kind of sales force do we need to deliver on the targets? So there's different types of salespeople. There's kind of client-facing sellers. There's technical sellers and so on. So what sort of mix do you need to optimize your revenue? Things like that. Which units are not performing well? Which sellers might miss their quota? And how can we align sellers with client opportunities? So yeah, just I mean, a kind of long list, but I just wanted to give you a sense of the broad sort of questions that might arise. So here are a few more. So who are the influencers of a product? Optimal marketing strategies. This one will actually talk about more, these two. So should we hire an employee? Which employees are most at risk of voluntarily leaving the company? And so on, future planning sort of things. Will outsourcing help? Things like that. Which company should we acquire? Okay. So now these are all business questions. It's not clear how this relates to electrical engineering. So let's see how that might be true. So we can, if we use appropriate data and signals as raw materials and then signal processing techniques to transform the raw data into meaningful descriptions, predictions, recommendations, and actions. So that's where this whole kind of signal processing stuff comes in. So it's not always obvious how. Some questions require just existing algorithms. You can just take them off the shelf, but others require some new research and so on. And once you actually do start getting involved with sort of business questions, then you do start seeing signal processing questions pretty much everywhere. And again, my view, so signal processing has been applied to lots of fields like radar and images and music and speech and so on, communications, but it hasn't been applied to business so much yet. And so now, I mean, there's this opportunity going forward of that we can look at these business problems and have people skilled in kind of this signal processing sort of techniques involved in those topics. Okay, So another point which I'll come back to later is when you are dealing with business applications, it's not just that you need good signal processing methods. So if you want to actually make an impact, so you need to actually make it such that other people, the stakeholders in the problem, will be able to operationalize any solution that you come up with. So these are kind of 3 steps that someone has come up with on how to operationalize sort of business analytics solutions. So first is, while you're doing it, then understand how the analytics will be used and develop the solution accordingly. The second is having transparency, trust, and confidence. So in that, the solution should explain why a recommended action is appropriate in terms that the stakeholders are familiar with. So that is what will actually be the motivating factor for us when we come to the decision rule learning part. And then there should be a clear interpretation of what action is recommended. So you can't say that, I mean, this is 25% more than this without saying, I mean, which one you should actually follow or stuff like that. So there's a bunch of factors that come in when you're doing research of this type that you need to take into account. Okay, so hopefully some motivation on kind of this whole general area of business analytics. So let me talk about a specific problem which we worked on within IBM to help the company. So the title is Proactive Retention, and I'll explain what that means. Okay, so as some more motivation here, this is from an article in the Wall Street Journal from last year. So Caesars Entertainment Corporation made a counterintuitive discovery when it was determining the effect of the pay that employees receive on their retention. So retention, again, is so people are employed, they might voluntarily resign or they might stay. So companies want to keep the employees that they have generally. So they found their attrition rate was around 16% for employees who earned less than the midpoint of their salary range. And then if they were able to bring an employee's salary up to the this midpoint of their salary range, then they could get their attrition down to 9%. And if they went beyond that, it actually had little to no benefit. So based on these insights, this company was now able to be very surgical in giving pay raises to its most prized workers. So they were able to kind of maximize the budget that they had to keep the people that they wanted.
But if you have additional information, such as, for example, let's say you rank employees into 3 groups: bottom quartile, top quartile, guys in the middle, or girls. Wouldn't you imagine that those percentages would be different for those 3 groups?
The base attrition rate, you mean?
Yeah, I mean, I would imagine. Okay, maybe now we're sort of in a weak economy; things are different. But I would imagine in equilibrium, people in the top quartile of performers, if you're paying them less than medium, 30-40% of them are going to leave. On the other hand, people in the bottom quartile, they're just pretty much happy to. That would be my assumption. I might be wrong.
Yeah, it is kind of along the lines that we will find in our IBM studies also. It's so when we apply this to the IBM population, we focused on the growth markets, so India and China primarily. In those countries, the economy is growing really fast. So there, people tend to jump companies very quickly, every like 8 or 10 months or within a year, because when they jump companies, they can get a salary increase of like 15 or 20%. Just by doing that. So that was the population that we were focused on within IBM for doing this project.
And maybe you can, maybe you're not allowed to answer, but are your ideas actually used to already differentiate salaries in IBM, or? Yeah.
So last year we gave pay, based on our research, IBM gave around 20,000 people pay raises. And they spent about $16 million on giving these pay raises. So yeah, it is in action. Everything that I'll talk about was implemented and so on. Yeah.
How about with this idea? applying DSP to business analysis?
Yeah, so I actually hadn't realized before I was looking for a job that you could apply sort of signal processing things to business problems. And then I sent my resume to the IBM Watson lab, and when I when I went there for the interview, it was with the business analytics department, and I didn't even know what business analytics was at that point, but it was very interesting for me to see how this could be done. And we actually have a large group of people doing these sort of things. And so, yeah, I mean, since I've been there, it's been about 3.5 or 4 years now. So, yeah, I mean, just understanding that every potential question that a large organization has some data and some statistical sort of insight related to it and signals and so on. So it's just, I mean, there's all sorts of problems out there that, I mean, once you start thinking the right way, it's definitely possible to apply techniques there. This particular problem, we were approached by the HR organization within IBM. They have known for a while about this retention problem in the growth markets. And there's a lot of reasons why trying to retain people is a good thing for IBM in those countries. So they knew that our group was involved with using data for this purpose, so then they came to us, which motivated the problem.
So compared with this department, there are data mining. So
yeah, so this is, I mean, data mining in signal processing. I mean, so my personal view of it is data mining approaches things from the bottom up. You start with the data and then see what you can get out of it, whereas signal processing thinking is usually more model-based. You imagine what the kind of the physical process is that's happening, and then you develop models based on that, and then once you get data later on, then you see how well your models match or not. And that's just my personal view on the distinction, but really you can say that data mining, computer science stuff, and this from a signal processing perspective are very similar also.
Just want to make sure I understand.
Yeah.
So for the second one, you said bringing an employee's salary up. Does it mean that for this experiment, you only test on one of the employee in the whole company?
No. So this is just from this Wall Street Journal article. Let me get to the actual thing. Yeah. Yeah. Okay. All right. Let me not talk about this then. I think we've kind of gone through things. So workforce analytics in general is specifically within this business analytics thing for human capital management, so the people that you have. So there's all sorts of stuff, skills and headcounts and recruitment and so on. And these days HR people think that retaining value talent is the most important thing in business, but let me not dwell on that. And we've all kind of already discussed this a little bit, but why do companies want to retain their employees? So it's costly for several reasons. One is when you lose an employee, you have to hire a replacement employee. There's loss of productivity while the new employee ramps up. There's hiring and onboarding costs, so you have to bring people in for interviews, you have to process the paperwork and all that sort of stuff. And this was what I mentioned before, in countries with rapidly growing economies, so if your employee left, they get a 15%, 20% salary bump, then you yourself, when you hire a replacement employee, will probably have to give an equivalent salary bump as well. So it's a huge cost in that sense. So companies would like to institute programs that reduce this voluntary attrition. And they don't want to just do blanket raises across. They want to do targeted ones. So it'll save a lot of money and it'll boost morale and things like that as well. Okay, so the overview of the techniques that we applied. So we have historical data of the entire IBM population, and since we were focusing in on growth markets, this was around 200,000 employees in the growth markets in IBM. So over a certain time period, we had labeled examples of employees that left and employees that stayed. And we had several types of features associated with these employees. So things like HR features, which organizational group you're in, which salary band you're in, how many years of service you have, a variety of things like that. Compensation features as well. So what your exact, salary amount is, how it relates to the market, things like that. And our task was to map individuals to attrition probabilities. So for that entire 200,000 strong population, we wanted to assign each person a probability of attrition. So the training data went back for a few years. We didn't want to use, we could have done more, but we wanted to use kind of current conditions. So then what we did was we trained some machine learning algorithms, and I'll show you an example later on, to find sort of classification rules that will give probabilistic outputs to map individuals to attrition probabilities. So again, it's not just for one person. So we do this at a large scale. Then we calculate the costs and benefits of the attrition and the retention. So for certain types of job roles, it's cheaper to find replacements. For certain job roles, it's the salary premiums aren't that high actually, and so on. So we basically look at the statistical analysis of base salaries of new hires in comparison to existing employees. Yep.
Have you also used this, let's say, if a person comes to their manager and says,
Yeah.
I've got another offer, I'm quitting. Have you also used this in how much of a salary bump will we offer this person to try to get them to stay?
Yeah, we didn't use it in that manner. It could be done, but the way this program was instituted was almost every employee was eligible for this salary raise, and our job was to identify the employees for which to give this external sort of salary raise to without any internal politics or anything like that. So that was our goal. Yeah. But I think it could be done the way you're saying as well. And then the retention actions that we had available in this program, at least, were only salary raises. So you could imagine other retention actions like promotions or bonuses or, just giving someone a pat on the back. Or, any sort of retention action could be considered. But in this case, we had 2 levels of salary increases. And then we want to optimally assign the retention actions to individual employees to achieve the best cost-benefit subject to a budget constraint. So yeah, we actually did all this stuff, and yeah, we did actually spend quite a bit of money. Yeah, so I think the current number is we spent $16 million, and the benefit we've received from it is like $50 million or something. So it's, it's a decent-sized activity, and basically everything that I said can be summarized in this sort of general system diagram, but I'm not going to go through the diagram itself. But the key point that I'm going to focus in on now going forward is this box, which is the determination of the individual level voluntary attrition risk patterns. And that, we'll see how we do that, and that's basically the machine learning sort of approach. Okay, so and specifically, we've been using predictive models based on compact rule sets composed of Boolean expressions. And the reason for that is that for business people, they're the most well-received and trusted because they can understand them very easily. So this is an example. It's not based on real data, but this would be a typical example of a rule predicting attrition among software salespeople. So if they're in a particular job role, so let's say specialty software sales rep, and their base salary is less than $75,000 per year, it's been more than 13 months since they're promoted, but less than 30 months since they're promoted, and they're not on a quota-based compensation plan, then we predict that they're at risk of voluntarily resigning. And we can also get probabilities, but let me not go into that. So just as a binary classification. So these are the types of rules that decision makers tend to like seeing because they can understand what exactly is going on. Yep.
So forgive me for interrupting all the time.
Sure,
but,
sure. Yep.
If I had a similar problem in another environment, I'll tell you about it later.
Okay.
But if you tell decision makers have a complicated function, I can give you this Boolean set thing. It'll save you, I don't know, $20 million.
Yeah.
I have this complicated function. As far as you're concerned, it's a black box. Instead of 20 million, it will save you 73 million.
Yeah.
Are they going to listen to you, or are they going to say, well, I don't understand this?
So it's a mixed experience. If the difference is 20 to 25 million, maybe they'll definitely go with the 20 million, I think, with the simpler understanding. If it's that large of a difference, it might be a different story. So our goal in the end is to get interpretable decision rules whose accuracy is as close as possible to the like the best you could do with any algorithm. So, I mean, it's really a mixed sort of thing. I mean, you can't generalize that for certain people that go different ways. So.
I'm going to comment on that. Sometimes companies need to defend their actions, say even in court,
Yeah.
and so they need to actually be able to present those things.
Right, and yeah, similarly, like, so let's say there's two employees who got pay raise. There's one that got a pay raise, the one that didn't. Then if the employees themselves then ask, like, why was this person given a pay raise and this person was not, then again, for them, not even just the decision makers, but the individual employees, you can then, I mean, we don't show them these, but if they wanted to, they could, understand these as well. Yeah, so black boxes would be like neural networks or SVMs, which we want to avoid in this situation. It also gives us actionable insights in the sense that promotions, salary increases, and changing compensation plans would be actions that might mitigate the voluntary attrition. Okay, so yeah, I'm not allowed to give all the statistics for like how much money we spent and like which populations we considered, but it is a very successful program within IBM. So now let me get to some actual technical stuff, which is not how we actually implemented this proactive retention, but from that whole experience, Dimitri and I were motivated to look at this technical problem of learning interpretable classification rules. Okay, so for anyone in the audience who is not familiar with the general supervised binary classification problem, let's just a very quick highlight. So it's the prototypical problem in machine learning. So you want to learn a decision rule from a set of independent training label training samples. And you want it this decision function not to do well just on the training samples, but to generalize well to new unseen data samples from the same distribution. So you have features X and labels Y. For our case, let's consider binary for simplicity. So you have labels either 0 or 1. So you have some training set, so X1, Y1 through XM, YM. And you want to learn this classification function Y hat, which is a mapping from X to this set 0 or 1. And you want to do it again so that it generalizes to new unseen samples. So there's lots of approaches to this binary classification problem. Some are heuristic, some are very principled and optimized. But in the end, I mean, there's no one best classification algorithm because it depends on the data characteristics that you have. And we want to focus here on interpretable rule-based classifiers. Okay, so just for kind of terminology, so a single rule is an AND clause of a few Boolean terms, like that the voluntary attrition rule that I showed. Another single rule would be in like a tennis example. So Federer defeating Murray if he wins more than 59% of 4-9 shot rallies and this and this. So these are all Boolean clauses that are ANDed together. And a rule set is a collection of single rules where we can combine single rules either by ORing them together or by doing a weighted combination of the single rules. Okay. So is that clear? Yeah, okay. All right, so the challenges of rule learning are, so finding compact decision rules involving a few Boolean terms that best approximate a given data set is an NP-hard combinatorial optimization problem. And most existing approaches maximize some heuristic criteria such as information gain, support, lift, and Gini impurity, and things like that. And also there's decision tree approaches and so on. So these are all sort of greedy heuristics with ad hoc pruning. So what we are interested in is have rule learning be driven by a principled optimization approach, which still retains interpretability, but hopefully approaches at least the classification performance of sort of black box approaches. Okay, so hopefully some or all of you are familiar at least with the general idea of compressed sensing and sparse signal recovery. So it's another problem where the core problem is NP hard. But in that problem, under certain conditions, we're able to solve it via convex relaxation. So that's the idea we'll apply to the Boolean rule learning as well. So we use recent ideas on Boolean compressed sensing and its relationship to Boolean group testing to propose a convex relaxation for the single rule learning problem in supervised classification. And we will obtain conditions for exact recovery. We'll also extend the approach to learn sets of rules and show some performance results as well, that we actually are able to get competitive performance in comparison to other classification algorithms while retaining interpretability. Okay, so the group testing problem, this is a statistics problem that's been around, I think, since World War II. So the idea is to discover a sparse subset of faulty items in a large set of mostly good items using a few pooled tests. So the original application was to test army recruits for syphilis. So there's a blood test for syphilis, but if you test each individual's blood sample, then it's very costly. But if you mix together a bunch of people's blood and test the whole sample together, then if it comes up positive, that means the OR of the set had syphilis. So at least one or more had syphilis. So if you can do this in a smart way, you can have a very small number of blood tests, but determine accurately which army recruits have the disease. And this also comes up in many other fields these days, in computational biology, fault discovery, and computer networks, and so on. So as I mentioned, if the test is negative, none of the recruits are diseased. If the test is positive, then at least one of the recruits is diseased. And so we want to do this in a smart way. So that's the group testing problem, and that is actually going to be related to how we do this Boolean rule learning as well. Okay, so how is rule learning similar to group testing? So we start off with the same setup of the binary classification problem, and now we construct individual Boolean clauses from the features x. So a sub j of x is some function that's a 0-1 function. So an example would be, is it true that the month since you were promoted is greater than 13? Or is it true that compensation plan equals the quota-based plan? And for continuous dimensions of x, we can have a bunch of thresholds from which we make comparisons to set up these a functions. So we have n of these Boolean functions from our feature set. And then we can calculate the truth value of each Boolean term for each training sample and construct an m by n truth table matrix A, where all the elements are this a sub j of x sub I.
So how do you determine the Boolean function A?
Yeah, so that is part of, like in any machine learning problem, you have to figure out what your features are beforehand. So that is not something that we're worried about here, but it is obviously very important. So in our voluntary attrition problem, I mean, we have some features that we know are related to attrition, like salary and promotion and stuff. So we include those. In the tennis one, I mean, if you understand a little bit about the game, then you can construct features in that way. But it's very problem specific of what the actual features should be. Once you have the general features, then constructing the Boolean versions of them, if they're categorical variables, you just create one for every possible outcome. If they're continuous, we threshold them. So yeah, just discretized. Yep. And we're working on an approach where we don't actually have to discretize, but that's kind of future work. Yeah. Okay. So now we have this big matrix A. It's a Boolean matrix. It's m rows by n columns. And it has, as I mentioned, the truth value for each feature that we have. Okay. Okay, so relating this back to the group testing problem, so in our training set, the samples that were positive, the positive training samples are equivalent to pools of diseased army recruits. So the OR of the features for that training sample goes back up and becomes a positive example. So what our task now is to determine an n×1 Boolean coefficient vector W that specifies which Boolean terms A sub j to OR together in a decision rule to recover the positive samples. So does that make sense? Yeah, okay. So just notationally, we want this W vector such that our training sample class labels Y are approximately equal to our truth table matrix A. And this notation we kind of made up. We didn't know what notation to use. So some sort of vector, matrix vector, or with this coefficient vector W. So it's really the Boolean equivalent of a matrix vector product. So we have the elements, we AND them together with the coefficient vector. So this is similar to multiplying, and then we add them up. So that would be like ORing them together to get the ith row for Y. And typically in classification problems for human interpretation, AND rules are more natural than OR rules. In what I'll present, these are all OR rules in the mathematics, but it's very easy to construct AND rules also using De Morgan's laws. So going forward, I'll stick with this OR, but know that it's very easy to get AND rules as well. Okay, so what is noise in this problem? So we have binary noise because everything is Boolean. So here, this is the exclusive OR operation. So Y is this A or W XORed with some noise vector, which again is a Boolean vector. And our task now is to find a classifier with a few Boolean terms in its expression. So this vector W should be mostly zeros with a few ones. So it should be a sparse vector. So we want it to be sparse both for generalization and for interpretability. So our problem then is to minimize the L0 quasi-norm of W such that Y equals A or W. Okay? And this L0 quasi-norm is just the count of the number of non-zeros. And since we're in a Boolean setting, it's just everything is 0 or 1, so it's a count of the number of ones. Okay. All right. So now coming to how we're actually going to solve this. So we use the ideas from sparse signal recovery in this context. So basis pursuit is a convex relaxation of L0 to L1, and it's very popular these days. So we want to minimize the L0 norm such that Y equals A. W is the signal, the sparse signal version of this without the Boolean stuff, and we relax it to the L1 norm. So now we have a Boolean algebra problem. So it's not exactly clear how to do this because just doing this will not maintain the sort of Boolean nature of the problem. But it's actually not that hard to do. Okay, so if we have a Boolean vector W that satisfies this Y equals A or W, then it also satisfies these two ordinary linear constraints. So if we denote the rows of A that correspond to rows of Y which are positive, then this A sub P times W, again, this is in the regular linear real valued algebra, is greater than or equal to 1. And this, again, is because when you OR things together, you can have more than one that are true. So if you have 1, 2, 3, 4, however many are true, that'll be reflected by this constraint. And if we have A sub Z being the rows of Y which are 0, then A sub z times W equals 0. So wherever, again, so when an OR operation is false, then you have identically 0 there. Okay. So through that, then we can set up this linear programming sort of approach. So first, before we do this, let's just do the Boolean version of the L1 problem. So we have the L1 norm that we're minimizing with these two constraints that I just described, and the W sub j's need to be either 0 or 1. So now, if we relax this, so we can get rid of this integer or Boolean sort of constraint, then we'll get a linear program, which is that the W sub j should be between 0 and 1. And if we introduce slack into the problem, so if there's noise, which there always is in the machine learning case, so we introduce slack variables, then we have this regularization parameter lambda, and we are able to obtain this noisy version of the linear program that we want to solve. Okay. All right, so we've described a convex relaxation. It'll find a solution, but is that solution any good or not? So we can actually get some exact recovery guarantees based on a definition that comes up in group testing. So the definition is that a Boolean matrix A is k disjunct if the union of any k columns does not contain any other column. Right, so you take a set of k columns, you look at all of them, and if you basically OR them together in a sense, then you don't end up with another column. So then our theorem is that if there is some W star where there are k non-zero entries, so it's k sparse, and you have y equals a or this W star. So if A is k disjunct, then the linear programming solution recovers the optimal W star. And with enough training samples, the matrix A will be k disjunct. So in practice, if you have a small sample situation, then A won't be k disjunct. But if you get enough samples, it will be. And usually in these machine learning problems, there's no real notion of exact recovery because there is no sort of exact W star that represents a true situation. So we also have some results on approximate disjunctness. So a Boolean matrix A is epsilon k disjunct if I guess this got shifted a little bit. So if n choose k of the if out of those n choose k subsets of columns, at least 1 minus epsilon of them satisfy the same thing that I said before, that their union does not contain any other column. So then the theorem is that the same thing. So if we have A being epsilon k disjunct, then the LP solution will recover W star with probability at least 1 minus epsilon. So just some theoretical results there. All right, so let me show some examples on some machine learning data sets as well. Right, so this is a data set from 1936 that's often used in various papers, not for anything else, but it's Ronald Fisher's iris data set. So originally it was a 3-class problem. You wanted to distinguish 3 different species of the iris flower. For our purposes, let's convert it to a binary problem. So we want to find the species versicolor versus the other 2 species. So we find this sparse solution to our convex relaxation, and this is what it looks like. So these are the 3 rules. So this is a 4-feature classification problem, but only 2 of the features come into the rules that we find. So it's that petal length should be less than or equal to 5.35 centimeters, petal width less than 1.7 centimeters, and petal width greater than 0.875 centimeters. So again, this is very interpretable. These are the, I forget if these are the training or the test samples. I think these are the test samples. So this is our rule, and then these are the versicolor species flowers, and these are the non-versicolor. So just as an example of what this is doing, but this isn't very convincing. I mean, it's a very easy sort of problem. So we also will show competitive performance results on a variety of data sets. before doing that, we also extended our approach to go from single rules to multiple rules, so sets of rules. So we used two approaches. One is the set covering approach, and the other is through boosting. So set covering works by you first learn the first rule. Whichever samples that it was wrong on, you only consider those in the next rule and learn the next best classifier on those and so on. So that's the set covering approach. Boosting is similar, but after every round you reweight the samples and give more weight to the ones that you got wrong in your previous rounds. And so with set covering, the rule set is an ORing together of all of the rules that you've learned. In boosting, it's a weighted combination. Okay, so on the next slides, I'll show some results on 8 standard data sets from the UCI machine learning repository. So we'll compare to a variety of rule-based classifiers and other classifiers as well. So we are able to achieve competitive accuracy with high interpretability, and among the rule set approaches, we're more accurate than decision lists and more interpretable than the C5 decision tree converted into a rule set. Okay. So these are tenfold cross-validation test errors on various data sets. So there is an example of a data set on, this is our single rule learner that we proposed. This is the rule set expanded using set covering, and this is with boosting. This is the decision lists algorithm, the C5 decision tree distilled to rules, classification and regression trees, tree bagger, K-nearest-neighbor, linear discriminant analysis, and SVMs. So these are all implementations either from MATLAB or from SPSS Modeler.
What is SVM?
SVM is a support vector machines. Yeah. So it's a very typical machine learning algorithm that is very frequently used and known to perform well.
So is this a linear SVM or is it kernel SVM?
This one is, it is a SVM with a polynomial kernel.
So how do you tune the parameters?
So these are all default parameters from the implementation. Either it's MATLAB or from SPSS Modeler, whichever one we got it from. I think that one was from, I forget which one it was from. You can look at the paper with all the details. I don't remember all the details offhand.
So another question is that,
yeah.
is those data sets balanced or balanced?
So some of these are imbalanced. So, I mean, you can look up the statistics of the different data sets. I know for sure with this ionosphere and Parkinson's disease and this PIMA and diabetes, they're fairly balanced. None of them were like hugely imbalanced. So yeah. So it turns out this this is another diabetes one. Our rule set learner with the boosting is actually gives the best accuracy, and even in comparison to some of the more complicated uninterpretable classification algorithms. But the more important note here is that we're fairly competitive regardless. So through our, even the single rule learner, the accuracies that we achieve are not far off from more like black box type approaches. And in terms of the interpretability, so if we compare the number of conjunctive clauses in the rule set, so if we compare to decision lists as an example, so we do have a few more rules. In the way we did the boosting, again, we didn't tune the number of rounds. We just fixed that to 5 rounds of boosting. Again, we could do it if we wanted to. So we have a similar number. It's not much more than the decision list, but our accuracy is always better than decision lists. So for every data set, all of our things have better accuracy than decision lists. And this is the SPSS implementation. C5, again, we're often in the same ballpark or better in terms of accuracy, and we're always much better in terms of the number of clauses in the rule set. So it increases the interpretability. Okay. Yeah.
But did you also compare the time, running time?
We didn't because this was our very poor MATLAB implementation, and that's actually something we're working on. So there are optimization experts within IBM Research that we're consulting. So since it is a linear program with a lot of structure, there are lots of tricks that we can do that will definitely improve the performance in terms of running time. So Cplex is something that we have tried running this with, and it's, I mean, to me it seems very fast, but the optimization guy who ran it for us, he said, oh, I can even do this 10 or 100 times faster if you give me some more time to work out what the structure of the problem is and stuff. So
I think maybe one of the better solver is stochastic gradient. So it's especially fit for this kind of a sparse problem.
Yeah, so the reason why we're using just kind of more generic LP solvers is because so when you have continuous variables and you're thresholding them, so really there is a lot of structure in the columns, because if something is greater than a certain threshold, then it's also greater than the next lower threshold and so on. So that truth table matrix has a lot of repetition, so you can do some transformations in order to zero out most of the values in that matrix. And then if you use the, kind of these LP solvers, then you can do a lot of things faster. Another thing that we're looking into is, so there's a concept of screening. So it's possible in the compressed sensing literature, the sparse signal recovery literature, to guarantee that certain columns will never appear in your optimal solution. So if we can expand that idea to our Boolean case, then we can know for a fact that certain columns will never appear. So again, we can take advantage of the structure. Yeah. So just to conclude, kind of summarizing the talk. So just the first summary, I guess, is on the first part of the talk, which is that business analytics is definitely an important endeavor that's behind the transformation of lots of businesses and companies today. And there's a lot of different business problems that can be approached through methods that statistical signal processing people are familiar with or work on. So it's definitely an area looking for innovative solutions that I think we can provide. And there's lots of interesting problems, both because of the applications themselves, the different types of data, the different relationships with business questions, and so on. And in particular, I showed you an example of a real-world problem, which was this proactive retention or voluntary attrition modeling stuff. And I mean, there's tons of other applications, interesting ones that I've been fortunate enough to work on. In terms of the rule classification-based stuff, so again, the motivation was that for stakeholder buy-in, we definitely need to have interpretable classification rules. And we could just use things that are out of the box, like we could use the existing rule learners, but since we're researchers, we thought we should do some research where we can actually get very good solutions, even better than the existing approaches that kind of use our skills in that sense. So instead of having heuristic sort of approaches that are typical, we'll propose an optimization-based method. If we view rule learning from the perspective of group testing and compressed sensing, then we can formulate this convex relaxation, get an LP with some exact recovery guarantees as well. And it actually does pretty well in terms of accuracy, and by construction it has good interpretability. And yeah, so some future work includes exploiting the structure of the LPs, as I mentioned, to be able to get fast solutions. And another point about why stochastic gradient descent might not be an ideal situation for us is because everything that we're doing, we want Boolean solutions. So when you're doing kind of gradient descent, you're going to have this little bit of noise and stuff. So there'll have to be some rounding at the end. But with the some of the solvers that we're trying to use, you by definition will only get integer solutions or binary solutions. So that could be another advantage of not using stochastic gradient descent. But I mean, we can definitely try it out.
What I mentioned is coordinate gradient. So basically, you just fix all the other coordinates. That's your features, right? Then you optimize one feature one by one. So basically, you shuffle it, then do the optimization. Then the problem becomes much simpler because you fix all the other features only update one coefficient. That can be one of the best algorithms for solving this everyone recognizes the convex optimization problem.
Okay.
It is also very fast.
Yeah, we can try it, certainly. Yep.
So I understand that the issue of the business people wanting to look at the data, you know, in Boolean rules, I understand their concern.
Yeah.
But I just want to mention that if you were to go back to the linear model, and maybe even things a bit fancier, which at the moment I can't really think about, this really resembles one-bit compressed sensing, where, you know, for each individual in your training set, you're getting a number like 1 or 2, meaning retainment, quit. Or even, you know, retainment, quit, remained at the company after a 10%, you know, salary offer, something like that. So, you know, that really resembles, you know, compressed sensing with a very, very, very small number of outcomes, and then you would be interested in learning the rules. So, so I think that's, you know, all these things are very related.
Yeah, I agree completely, definitely. Yep.
Any other questions?
And where you get the errors? The errors you mentioned.
Sorry?
From the where you get the errors.
Which errors?
You mentioned in the charts.
You mean?
From the LP noise you mentioned before.
You mean like these?
Yeah.
Yeah, so these are standard data sets where you actually have the full data set that's labeled. And the way tenfold cross-validation works is that you train on 9/10 of the data, and you test on the remaining 1/10 that you didn't include in your training set, and you do it for all 10 potential splits, and then you average them together.
Is there anything to do with the LP noise?
I don't really. So say that again.
Anything to do with the LP noise?
No. So these. I mean, the solution always is the optimal solution that we're finding because when we're doing this machine learning problem, we are training on one set of data, and then we want to generalize to new unseen data. So no matter what, there will be generalization error because you can never perfectly understand the distributions and then apply them to new data. So just by the matter of fact that we have finite training samples, there will be error. And even if we had an infinite number of samples, the lower limit here would be the Bayes optimal sort of decision classification performance, which would, again, be related to how overlapped the distributions are for the different classes.
So another question is that when you do prediction, do you do you first recover the rules, then use those rules to do prediction, or you use the numerical variable you generate, for example, the decision boundary you generate to do the prediction?
It's equivalent for us because all our rules are binary splits, so they are the decision boundary.
And the error is your conclusion, right? But is your result? The error should be a result of this analysis.
I mean, in our view, it's good that the accuracies are decent. For us, it's the more like the idea that you can use these sort of sparsity ideas for rule learning, I think, is the bigger story. We didn't spend hours and hours trying to do anything with the actual performance. We just tried doing something and it works reasonably. So yeah, I think just the fact that you can look at a classification problem with interpretable rules through this group testing or this Boolean compressed sensing, I think, is the main thing.
So from which result you get your conclusion in the characterization?
I didn't understand. Say
I mean, from which result you make this decision according to it? As a company, just like.
So this is one classification algorithm that we're proposing. In the previous section, when I talked about the proactive retention, we didn't actually use any of these. We used something else. Yeah, I mean, that was a motivating factor for us that we should develop some principled algorithms that would give interpretable rules as an output.
Any other questions?
Yeah.
Okay.
So just I want to clarify. So
Yeah.
once your algorithm,
Yeah.
you train your algorithm, you
Yeah.
get a weight vector W that
Yeah.
is actually contains continuous value, right?
No, it's going to be 0, 1.
But you already relaxed the W. You relaxed that part.
Yeah, that's right. In most situations, it will give a 0, 1 vector as the optimal solution, but there will be cases when it's not, so we use randomized rounding in that case.
So basically, you get like a contain because that vector will be very sparse and
Yeah.
contain continuous value, but then you do random run up then to 0 or 1, right?
Yeah, in the typical case, we actually get integer solutions. So all of the entries of W typically are either 0 or 1, but there can be some cases where that doesn't happen. In that case, we use randomized rounding.
I have one question.
Yeah.
I get maybe you did take into account one factor, which I think actually is perhaps an important one, is and you didn't mention anyway, is the job satisfaction.
Yeah.
Because there are people basically
Yeah.
monetary thing doesn't
Yeah,
mean anything.
that's right. Yeah, so we can only do as well as our data allows us. So we don't capture data about, like, if your spouse is moving to another city, that means that you're likely to leave. I mean, we can only work with the features that we have access to. So one feature that people cite a lot, that your commuting time is a very big predictor in whether you are leaving or staying in a job. We don't have access to that information, for example. So yeah, we could do better if we had more kind of information, but it's not available to us.
On the other hand, that's much harder to capture too.
Yeah.
Quantitatively, that is.
Yeah. Right. So we can only do as well as the data allows.
Is it even legal for you to use data such as my employee is married or not?
We don't capture that either. We don't know whether you're married or not. We do know the gender of the employee, but that's not a feature that we could include, for example.
Oh, so that's not legal.
No.
All right, let's thank our speaker. So, you're going to be in your office?